Welcome. We are beginning a new lesson today, differentiation. Here are the objectives that we look forward to achieving at the end of the lesson. At the end of the lesson, you should understand the concept of differentiation. You should be able to differentiate a function from first principles. You should be able to differentiate a function using the general rule. You should be able to differentiate a function using the product rule, the quotient rule, and the chain rule. You should be able to differentiate an implicit function. And you should be able to find a higher derivative. This lesson covers the basic concept of differentiation and how to differentiate a function. In this lesson on differentiation, we will be applying a lot of the basic mathematics knowledge we have gained so far. We will be applying some of the knowledge we've gained in the lesson on algebraic expressions, indices, fractions, equations, straight lines, quadratic functions, and graph of quadratic functions, and limits. So if you have to revise those lessons, I would advise that you revise them before studying this lesson, because we will be applying a lot of the knowledge we gained in those lessons here. Now let's learn about differentiation. The idea of differentiation is based on gradient. In the lesson on straight lines, we learned how to find the gradient of a line. Let's say this is our xy plane and we have a straight line in the plane. Let's say that we have 2 points, point A with coordinates x1, y1, and point B with coordinates x2, y2. When we trace the coordinate of point A, when we trace point A to the x-axis, we will get the x-coordinate, which is x1. When we trace it to the y-axis, we get the y-coordinate, which is y1. When we trace point B to the x-axis, we get the s-coordinate, which is x2. We trace it to the y-axis, we get the y-coordinate, which is y2. Using this information, we can find the gradient of the line AB, or the gradient of the line joining the 2 points A and B. We know that the gradient is the change in y divided by the change in x. So here the change in y will be the difference in the y-coordinates. That will be y2 minus y1 divided by the change in x will be the difference in the x-coordinates, which is x2 minus x1. We learned this basic concept in the lesson on straight lines. Now let's apply this to a curve. Let's say this is a curve, and the equation of this curve is y is equal to f of x. So the equation of the function is giving us y is equal to f of x. Now let's say that we have a point here, point A, and another point here, point B. When we trace the coordinate of A to the x-axis, we will get the x-coordinate. When we trace it to the y-axis, we get the y-coordinate. You see, the function is y is equal to, the function of the curve is y is equal to f of x. And here we have the y-coordinates, and we know that y is equal to f of x, so you can replace y with f of x. Okay. Now let's come to point B. We know that when we trace point B to the x-axis, we'll get the s-coordinate of point B. But let's consider something. Let's assume that the horizontal distance between point A and point B is h. The horizontal distance between point A and point B is h. You see, in the xy plane we have here, this point will be the origin with coordinates 0, 0. And we know that from the origin to this point is x, right? From the origin to this point, the distance from the origin to this point is x. And we are saying that the horizontal distance between point A and point B is h. So the horizontal distance between A and B is h. That means that the x-coordinate here will be x plus h. It will be the distance from the origin to x plus the horizontal distance between A and B. So that will be x plus h. Now for the y-coordinate, we know that the function is y is equal to f of x. And we now have the x coordinate here to be x plus h. So when we substitute it here, that is when you find f of x plus h, it should give us the y coordinate of point B. So the y coordinate of point B can be written as f of x plus h. Okay. Now let's assume that we draw a straight line to join point A to point B. So we have this straight line here joining point A to point B. From the lesson on straight lines, we know that using this information, we can find the gradient of the line joining point A to point B, because we know that the gradient is equal to the change in y divided by the change in x. So here the change in y will be the difference in the y coordinates. So f of x plus h minus f of x, that will be the change in y, divided by the change in x, which will be x plus h minus x. On the denominator, we have x plus h minus x, so x minus x is 0. And so this becomes f of x plus h minus f of x divided by h. Now, here is where it gets very interesting. Let's consider something. Let's say that we want the horizontal distance between point A and point B, which is h, to be as close to 0 as possible. We want it to be as close to 0 as possible. We don't want it to be 0. Rather, we want it to be as close to 0 as possible. One way of doing that is by dropping the point B, right? Dropping it down the slope. So I'm going to show you a diagram of it here. You see, we will drop B from this point. We will drop it and so that it gets closer to A, as you can see here. You see, on the diagram here, there is some distance between A and B, okay? But imagine that the distance is very, very, very small. In fact, it is very close to A, but not A, okay? Now, when you do that, as you can see, H gets very, very, very small. You see, as B gets closer to A, that is, as the horizontal distance H gets very close to 0, you can see that the gradient of the line joining point A to point B almost becomes the gradient of the curve at A. If you remember, in the lesson on graph of quadratic functions, we learned how to find the gradient of a curve at a point. In that lesson, we learned that if you want to find the gradient of a curve at a point, you draw a tangent to the curve at that point, then you find the gradient of the tangent. So here, if B gets very close to A, that is almost A, then the gradient of the line AB almost becomes the gradient of the curve at point A. So as you can see, as h gets closer to 0, the gradient of the line AB, that's the gradient of the line joining point A to point B, becomes or is equal to the gradient of the curve at A. This is very, very important because this will form the basis of everything we are going to learn here. As h gets closer to 0, or as h approaches 0, the gradient of the line AB is equal to the gradient of the curve at A. In the lesson on limits, we learned how to describe a function as it approaches a certain value. Here, we have learned that as h approaches 0, the gradient of the line AB is equal to the gradient of the curve at A. We already have the gradient of the line AB. So we can find the gradient of the line AB as h approaches 0. From the lesson on limits, we know that we can write that as the limit of the function f of x plus h minus f of x divided by h as h approaches 0. Remember, the gradient of the line AB is f of x plus h minus f of x divided by h. So the value of the gradient of the line AB as h approaches 0 can be written as the limit as h approaches 0 then the gradient of the line AB, which is f of x plus h minus f of x divided by h. This will become the gradient of the curve at A. So the gradient of the curve at A is equal to the gradient of the line AB as h approaches 0, which is the limit as h approaches 0, f of x plus h minus f of x divided by h. This is very, very important. Let's talk more about it. The gradient of the curve at A is equal to the limit as h approaches 0 of the function f of x plus h minus f of x divided by h. This is known as the gradient function. That is, the limit as h approaches 0, f of x plus h minus f of x divided by h is known as the gradient function, the differential coefficient, or simply the derivative. So anytime we are asked to find the gradient function, the differential coefficient, or the derivative, this is what we are asked to find, or this is what we have to find. This differential coefficient or gradient function or derivative can be denoted as dy dx or f prime of x. So this can be written as dy dx, which is the same as f prime of x, and this is equal to the limit as h approaches 0 of the function f of x plus h minus f of x divided by h. When you write it as dy dx, the notation is known as the Leibniz notation. And when you write it as f prime of h, it's known as the functional notation. In most of the questions that we will solve in this lesson on differentiation, I'll be using the Leibniz notation. But once in a while, I'll also use the functional notation. So when you use dy dx, it's known as the Leibniz notation, and when you use the f prime of x, it's known as the functional notation. Either of them is the same thing. You are being asked to find the gradient function, the differential coefficient, or the derivative. Now, when you use the limit as h approaches 0 of the function f of x plus h minus f of x divided by h to find the gradient function or the differential coefficient or the derivative, it is known as finding the derivative from first principles. It's known as finding the derivative from first principles. So we are going to learn how to use this to find the derivative. That is, we are going to learn how to find the derivative from first principles. We will consider a couple of questions. Let's consider the first one. Find from first principles the derivative of f of x equal to 5x. We have just learned that the derivative or the differential coefficient or the gradient function will be given by the limit as h approaches 0 of the function f of x plus h minus f of x divided by h. So here, to use this, we will first have to find f of x plus h. We already have f of x, so you get f of x. Then we will subtract f of x from f of x plus h. We will divide it by h. Then we will find the limit as h approaches 0 of the resulting function. Okay, so let's do that. The function is f of x equal to 5x. So we have f of x. Now we need f of x plus h. What that basically means is that we will take the function 5x, and wherever we see x, we will replace it with x plus h. So when you find the function f of x plus h, you have 5 into bracket. You see we have x here, so we replace it with x plus h. So 5 into bracket x plus h. When you expand this, you have 5x plus 5h. We learned this in the lesson on functions. So if you want more clarification on this, you can go to the lesson on functions and study more. Now we have f of x plus h, we have f of x, and so we can subtract and find the numerator here. When we do that, we have the dy dx will be equal to the limit as h approaches 0. The numerator is f of x plus h, which is 5x plus 5h, minus f of x, which is 5x, and you divide this one by h. 5x minus 5x is 0. And so this gives us the limit as h approaches 0, 5h divided by h. H cancels h, and so this gives us the limit as h approaches 0, 5. In the lesson on limits, we learned that when you find the limit of a function as it approaches a certain value, and the function is a constant, the limit will always be the function. So here the limit of 5 as h approaches 0 gives us 5. What it means is that the derivative of the function f of x is equal to 5x is 5, or the gradient function of the function f of x is equal to 5x is 5, or the differential coefficient of the function f of x is equal to 5x is 5. So when you differentiate the function f of x is equal to 5x, you are going to have 5. And that is why dy dx, which is the Leibniz notation, or the functional notation, which can be written as f prime of x, is equal to 5. So the dy dx, which is equal to the f prime of x, is equal to 5. So when you differentiate the function f of x is equal to 5x, you have 5. But here we differentiated from first principles because we used the limit as h approaches 0, f of x plus h minus f of x divided by h. Let's consider another question. Find from first principles the derivative of f of x is equal to x plus 2 squared. Okay. We know that from first principles, we are going to use the limit as h approaches 0. That is for the dy dx, or the gradient function, or the differential coefficient, or the derivative will be the limit as h approaches 0, f of x plus h minus f of x divided by h. We have f of x to be x plus 2 squared. So what we have to do now is to find f of x plus h. Then we will subtract f of x from it. We divide it by the denominator h, and then we find the limit as h approaches 0 of the resultant function. So let's find f of x plus h. Now here, we will have to, because this is a squared, we will have to expand it. So we have x plus 2 squared. When you expand it, you have x squared plus 4x plus 4. We can now find the function f of x plus h. So wherever we see x in f of x, we replace it with x plus h. So here we have x squared, and so it's going to be x plus h squared, then plus 4x. We replace x here with x plus h, so 4 times x plus h since it's a binomial, and then plus 4. Now let's do this expansion. When we expand x plus h squared, we are going to have x squared plus 2hx plus h squared. In the lesson on algebraic expressions, we learned how to do these expansions, and that's why I'm expanding them straight away here, because I know you know how to do all of this by now. When you expand 4 into brackets x plus h, you have 4x plus h, and then we have plus 4 here. Okay. Now we have f of x plus h, and we have f of x, so we can do the subtraction. So we are going to subtract f of x from f of x plus h. That will give us the numerator here. The function f of x plus h is x squared plus 2hx plus h squared plus 4x plus 4h plus 4. Then we are subtracting f of x from it. F of x has 3 terms, so we have to bring the bracket here to show that the negative affects everything in the bracket. Now let's expand the bracket here. When you expand the bracket, you have x squared plus 2hx plus h squared plus 4x plus 4h plus 4 minus x squared minus 4x minus 4. Okay. We can cancel out some common factors. X squared minus x squared gone. We have 4x minus 4x gone. 4 minus 4 gone. And this gives us h squared plus 2hx plus 4h. So the numerator here, we have h squared plus 2hx plus 4h. Now we can find the dy dx. the dy dx will be equal to the limit as h approaches 0. The numerator we had h squared plus 2hx plus 4h divided by h. We can see h is a common factor on both the numerator and denominator, so we can factor it out on the numerator so that we can cancel. When you do that, you have h into bracket h plus 2x plus 4. Now h and h should be gone, and so we have the limit as h approaches 0, h plus 2x plus 4. In the lesson on limits, we learned that to find the limit of this function as h approaches 0, we will substitute h is equal to 0 into it. So where we see h, we replace it with 0. When we do that, we have 0 plus 2x plus 4. And this gives us 2x plus 4. So this means that the derivative or the differential coefficient or the gradient function of the function f of x is equal to x plus 2 squared is 2x plus 4. So when you differentiate the function x plus 2 squared, you're going to have 2x plus 4. Let's consider another question. A function of f is defined by f is such that x gives us x squared minus 2x. Find from first principles the derivative of f. Okay, so we are going to differentiate this function from first principles. We know that to differentiate from first principles, we are going to use the limit as h approaches 0, the function f of x plus h minus f of x divided by h. So you first have to find f of x, which the question has given to us. We have f of x equal to x squared minus 2x. So we will need to find f of x plus h. To get f of x plus h, wherever we see x, we replace it with x plus h. When we do that, we have x plus h squared minus 2 into bracket x plus h, and this will be equal to, when you expand x plus h squared, you have x squared plus 2hx plus h squared. When you expand negative 2 into bracket x plus h, you have negative 2x minus 2h. Now we have f of x plus h, so we can subtract f of x from it to get the numerator here. When we do that, we have f of x plus h minus f of x will be equal to, we have found f of x plus h. We had x squared plus 2hx plus h squared minus 2x minus 2h. Now we are going to subtract f of x from it. So minus into bracket x squared minus 2x. We will expand this bracket here. When we do that, we have x squared plus 2hx plus h squared minus 2x minus 2h minus x squared plus 2x. There are some common terms that we can cancel. We have x squared minus 2 minus x squared will be 0. Negative 2x plus 2x will be 0. And so we will be left with h squared plus 2hx minus 2h. So that's what we have for the numerator. Now let's find our dy dx. The dy dx will be equal to, the numerator is h squared plus 2hx minus 2h. The denominator is h. As you can see, h is a common factor on both the numerator and the denominator, so we can factor it out and cancel. H and h will be gone, and this will give us the limit as h approaches 0, h plus 2x minus 2. To get the limit here, we will replace h with 0. So this will give us 0 plus 2x minus 2, and this gives us 2x minus 2. So what it means is that the derivative of the function f of x is equal to x squared minus 2x is 2x minus 2. So the derivative or the gradient function or the differential coefficient is 2x minus 2. So far we have learned about the basic concept of differentiation, what it means to differentiate a function. We have also learned how to differentiate a function from first principles. But as you can see, differentiating a function from first principles is quite lengthy. Anytime we are asked to differentiate a function from first principles, we have to go and quote this formula here, dy dx is equal to the limit as h approaches 0, f of x plus h minus f of x divided by h. This is quite lengthy. There is a general rule for differentiating a function. We are going to learn about that general rule. You don't always have to differentiate from first principles. In some questions, you may be asked to differentiate from first principles, but in other questions, you will just be asked to differentiate a function. And when you're asked to differentiate a function, you can use the general rule for differentiating the function. We are going to learn about that general rule and how to use it to differentiate a function. We are going to learn how to differentiate a function using the general rule. So you differentiate a function, but this time we are not going to differentiate from first principles. If you have a function and it's of the form y is equal to ax exponent n, where a and n are constants, so x and y are the variables and a and n are constants, then when you differentiate y with respect to x, we are differentiating y with respect to x. That is, when you find dy dx, you are differentiating y with respect to x. It will be given by n ax exponent n minus 1. So look at it. The exponent n will drop and multiply ax to get nax. Then you reduce the exponent n by 1. If the function is of the form y is equal to ax exponent n, when you differentiate y with respect to x, that is when you find dy dx, which can also be written as f prime of x, then you are going to have nax exponent n minus 1. The exponent n will drop and multiply ax, and then you reduce the exponent n by 1. Let's apply this to a few examples here. So let's say we have y is equal to 2x exponent 3. And we are differentiating y with respect to x. So we are finding dy dx, which is the same as f prime of x. The dy dx will be equal to 3 times 2x exponent 3 minus 1. So the 3 will drop and multiply 2x. Then you reduce the exponent on x by 1. So that will be 3 times 2x exponent 3 minus 1. 3 minus 1 is 2. So we have 3 times 2x squared, and that gives us 6x squared. When you differentiate this from first principles, you realize that you have 6x squared. So you see, using this general rule, we don't necessarily have to differentiate from first principles. Okay. Let's consider another one. Let's say we have y is equal to 5x, and we are differentiating y with respect to x. If you remember, we differentiated this from first principles and we had 5. Now we are going to use the general rule to differentiate. So let's go through it. You see here, the exponent on x is 1. That's why we don't write it. So we have 5x exponent 1. So what will happen is that the exponent on x, which is 1, will drop. Okay, so you have 1 times 5x. Then you reduce the exponent on x, which is 1, by 1. So that would be x exponent 1 minus 1. 1 minus 1 gives us 0. So you have 1 times 5x exponent 0. X exponent 0 is 1. So you have 5 times 5 times 1, which gives us 5. So as you can see, using the general rule, we have been able to find the derivative just as we did when we differentiated from first principles. So when you differentiate y is equal to 5x, you have 5. Here is a trick that you should note. Anytime you differentiate a function of the form y is equal to ax, if you have a function of the form y is equal to ax and you differentiate y with respect to x, so you find dy dx or f prime of x, you are going to have a. So look at it. If the function is such that x has an exponent of 1 and a coefficient of a, when you differentiate y with respect to x, the x will be gone and you'll be left with the coefficient. That's why here, when you differentiate y with respect to x, the x will be gone and you'll be left with 5. So let's say if I have y is equal to negative 2x, if I find dy dx, I'm going to have negative 2. The x will be gone and I'll be left with the coefficient. If I have, let's say, y is equal to x and I differentiate y with respect to x, the x will be gone and I'll be left with the coefficient of x, which is 1. So anytime you differentiate a function of the form y is equal to ax, the x will be gone and you'll be left with the coefficient, which is a. Okay. We will need this when we are doing more complex differentiations. Let's consider another example here. Let's say you have a function of the form y is equal to 3, and we are differentiating y with respect to x. As you can see from here, there is no x. There is an x, but x has an exponent of 0. So you can write this as y is equal to 3x exponent 0. Then we use the general rule to differentiate. When you use the general rule to differentiate, the exponent will drop, so we have 0 times 3x, then we reduce the exponent on x by 1, so we have 3x exponent 0 minus 1. But since it's been multiplied by 0, the whole thing becomes 0. Okay. Now here is another trick. If you have a function of the form y is equal to a, where a is a constant, when you find dy dx, you get 0. So we have learned two tricks here. If you differentiate a function of the form y is equal to ax, you get a. The x will be gone and you'll be left with a. When you differentiate a constant, you get 0. So anytime you differentiate a constant, you have 0. We will need these two a lot when we are doing complex differentiations. Now we are going to apply what you have learned here to differentiate some functions. There's one more thing that you have to note. If you have a function that is a sum or a difference, that is, when you have a function where you have more than one term being added or subtracted, you differentiate each of the terms separately. Okay. Now let's consider some examples. Differentiate the following. We have 1, 2, 3, 4, 5, 6 examples here. We are going to take them one after the other. Let's consider the first one. Y is equal to x cubed minus 2x squared plus 1. As I've already said, we are going to differentiate the terms one after the other. So we take the first term, which is x cubed. We are going to differentiate x cubed. From the general rule here, 3 will drop, then we will reduce 3 by 1. When you do that, you have 3x squared. Then we come to the next one. We have minus 2x squared. 2 will drop, so you have negative 2 times 2x. Then you reduce the exponent on x by 1. So that will be negative 4x, because you have negative 2 times 2x exponent 2 minus 1. And 2 minus 1 gives us 1. So you have negative 2 times 2x, which will give us negative 4. And then the third term. The third term is a constant, which is 1. Remember that I said that when you differentiate a constant, you have 0. So here, when you differentiate 1 with respect to x, you are going to have 0, so plus 0. And 3x squared minus 4x plus 0 will give us 3x squared minus 4x. So when you differentiate the function y is equal to x cubed minus 2x squared plus 1, you have 3x squared minus 4x. Let's consider the next example. The next example is x squared minus 1 divided by x cubed. As you can see from here, we have a quotient, a division. We are going to use our knowledge of indices to write this without the division sign. You see, from indices, we learned that if we have 1 divided by a exponent n, it can be written as a exponent negative n. So here, this can be written as x squared minus x exponent negative 3. Okay. Now that we have it without a division sign, we can apply the general rule for differentiation here. This is a difference, it's subtracting, so you differentiate each term. Let's do the first one. We are going to differentiate x squared. We are differentiating x squared. The 2 will drop, so you have 2 times, then x exponent, you reduce the exponent, which is 2, by 1, so 2 minus 1, and that will be 2 times x exponent 1, which is 2x. So when you differentiate x squared, you have 2x. Let's look at the next term. The next term is negative x exponent negative 3. Okay. When we apply the general rule here, the negative 3 will drop, so we have negative 3 times negative x. Then we will subtract 1 from the exponent, so that will be negative 3 minus 1. And when you multiply this, you have 3x exponent negative 4. Remember, negative 3 times negative x will give us 3x, positive 3x. So this will give us 3x exponent negative 4. So when you differentiate this, you have 3x exponent negative 4. From indices, we know that we can write this as 2x plus 3 divided by x exponent 4. We learned this in the lesson on indices, so if you want more clarification, you can go to that lesson and study more. Let's consider the next question. You have y is equal to x plus 1 times x minus 4. We have not learned how to differentiate a product yet. So here, to differentiate this function, we will first expand the bracket and then we will differentiate each term. When you expand this bracket, you have x squared minus 3x minus 4. Now we can differentiate each term. Let's differentiate the first term, which is x squared. When you differentiate x squared, you have 2x. 2 will drop and multiply, then reduce the exponent 2 by 1, so that gives us 2x. When we differentiate negative 3x, we will have negative 3. Remember, when you differentiate y is equal to ax, the x will be gone and you'll be left with a. Here we have negative 3x, so the x will be gone and you'll be left with 3. Negative 4 is a constant, so when you differentiate that, you get 0. So dy dx will give us 2x minus 3. Let's consider the next example. The next example here is y is equal to square root of x. Okay, it's getting quite interesting now. From indices, we know that square root of x can be written as x exponent half. Okay, now we can differentiate this. When we apply the rule here, when you differentiate y with respect to x, the exponent, which is half, will drop and multiply. So you have half times x exponent, then you reduce the exponent on x by 1. So half minus 1. So that's what we have here. You have half times x exponent half minus 1. And half minus 1 is negative half. Okay. Now this, from indices, we know that can be written as 1 divided by 2x exponent half. And x exponent half is square root of x. So this can be written as 1 divided by 2 root x. As I said, I explained all of this in the lesson on indices. So if you study the lesson on indices, you understand what we are doing here. If you have half x exponent negative half, it can be written as 1 divided by 2x exponent half. And x exponent half is square root of x. So this gives us 1 divided by 2 root x. Let's consider the next question. For the next question, we have y is equal to 3x squared plus 2 divided by x. From indices, we know that this can be written as y is equal to 3x squared plus 2x exponent negative 1. This is a sum, so you differentiate each term. You differentiate the first term, which is 3x squared. When you do that, you have 6x, because 2 will multiply 3x, and then you reduce the exponent 2 by 1, so that gives us 6x. Now for this, negative 1 will multiply this, and then you reduce negative 1 by 1. And so that gives us negative 2x exponent negative 2. Okay. And from indices, we know that this can be written as 6x minus 2 divided by x squared. Okay. Let's consider the next question. The next question is y is equal to 1 divided by the cube root of x exponent 4. Okay, this is quite interesting. From indices, this can be written as 1 divided by x exponent 4 divided by 3, because we know that the cube root of anything is that thing exponent 1 divided by 3. So the cube root of x exponent 4 is basically x exponent 4 raised to the power 1 divided by 3. And this can be written as x exponent 4 divided by 3, as you can see from here. So 1 divided by the cube root of x exponent 4 is 1 divided by x exponent 4 divided by 3. Now, let's continue. We know that from indices, this can be written as x exponent negative 4 divided by 3. Now we can use the general rule to differentiate. Remember, if you are using the general rule to differentiate, the exponent, which is negative 4 divided by 3, will drop and multiply. So we have negative 4 divided by 3, then times x exponent, we reduce the exponent by 1. So negative 4 divided by 3 minus 1. Negative 4 divided by 3 minus 1 gives us negative 7 divided by 3. So the dy dx will be equal to negative 4 divided by 3 x exponent negative 7 divided by 3. This can be written as negative 4 divided by 3x exponent 7 divided by 3. X exponent 7 divided by 3 is basically the cube root of x exponent 7. So 3x exponent 7 divided by 3 can be written as 3 times the cube root of x exponent 7. And so this whole thing becomes negative 4 divided by 3 times the cube root of x exponent 7. As you can see, we are applying a lot of the things we learned in the lesson on indices here. So I would advise that if you need to revise that lesson, you can go and revise it so that you understand what we are doing here. So far, we have learned how to differentiate when you have a sum or a difference. That is when the function contains more than one term and they are either adding or subtracting. Now, we are going to learn how to differentiate when the function is a product. That is when you have two terms that are multiplying. How do we differentiate it? Differentiation of a product. Let's consider the function y is equal to x plus 1 times x minus 4. We differentiated this function as part of the questions that we solved. You see, this is a product. We have two terms multiplying. The first one is x plus 1 and the second one is x minus 4. One way of differentiating this is by expanding the bracket and then differentiating each term. That's correct. But since this is a product, that is two terms multiplying, you can also differentiate it as a product. We are going to learn how to do that. Let's say that we have a function of the form y is equal to uv, or y is equal to u times v, where both u and v are functions of x. So you have two functions of x multiplying just as we have here. If this is the case, then the differential coefficient or the derivative or the gradient function dy dx, which can also be written as f prime of x, will be given as u dv dx plus v du dx. Dy dx will be equal to u dv dx plus v du dx. Now, how do we use this? Okay. What you do is that when you are given the product, you will let 1 be equal to u and 1 be equal to v. So in this example, we have y is equal to x plus 1 times x minus 4. See, we have two terms multiplying here. So you let 1 to be equal to u and 1 to be equal to v. So let's say we will let x plus 1 be equal to u and then x minus 4 be equal to v. Now when you do that, you now find du dx. So you differentiate u with respect to x. Then after that, you find the v dx. You differentiate v with respect to x. Then when you are done, you will be able to use this formula to find the derivative. Someone might say, why go through all this trouble? Why don't we just expand the bracket and differentiate as we did in the previous examples? That's true. That will work in most cases, but sometimes in some examples it is easier to use the product rule. That's why we have to learn how to differentiate using the product rule. So in the examples that we are going to consider next, we will differentiate some products, but this time you use the product rule. Let's consider these examples. We have y is equal to x plus 1 into bracket x minus 4. That's the first one. And then we have 3 more questions. So let's consider the first one. Y is equal to x plus 1 times x minus 4. The product rule is dy dx is equal to u dv dx plus v du dx. So what we will do is that we will let the first one be equal to u. So u to be equal to what we have in the first bracket, which is x plus 1, and v to be equal to what we have in the second bracket, which is x minus 4. So now we have u, we have v. Okay. From the formula, we need u, we need v, we need du dx, we need dv dx. So what we will do is that to get du dx, we will differentiate u with respect to x. So you see here, the function is u is equal to x plus 1. So we can differentiate u with respect to x. Okay. And then we also need the v dx. So you differentiate v with respect to x. Let's start with the first one, which is du dx. The function is u is equal to x plus 1. So we are differentiating u with respect to x. We start by differentiating x. Remember that if we have a function of the form ax, when we differentiate it with respect to x, the x will be gone and we'll be left with a. So we'll be left with the coefficient of x. Here we have x. The coefficient of x is 1. So when the x is gone, we'll be left with 1. 1 is a constant, so when you differentiate 1 with respect to x, you get 0. So when you find du dx, you get 1. Let's come to the second one, which is v. V is equal to x minus 4. Once again, when you differentiate x with respect to x, because it's of the form ax, the x will be gone and you'll be left with the coefficient of x, which is 1. Here the coefficient of x is 1. Negative 4 is a constant, so when you differentiate it, you get 0. So dv dx is also 1. So now we have u, we have v, we have du dx, we have dv dx. We can fix it in this formula to get our dy dx. So the dy dx will be equal to u is x plus 1, dv dx is 1. So you have 1 times x plus 1, then plus v is x minus 4, du dx is 1. So you have 1 times x minus 4. This gives us x plus 1 plus x minus 4, and this gives us 2x minus 3. So just as we had when we expanded the bracket and then differentiated each term, when you use the product rule, you get the same thing. In an exam, when you are asked to differentiate this, you can quickly just expand the bracket and differentiate each term. You don't necessarily have to use the product rule, unless the question specifically says that you should use the product rule. Okay. Let's consider the next question. Let's say we have y is equal to 1 divided by x squared times 3 plus 5x plus 2x squared. Once again, in this question, you can expand the brackets and then differentiate each term just as we did in the previous examples. But here, we are going to use the product rule. So here, the product rule says that dy dx will be equal to u dv dx plus v du dx. We have two terms here multiplying. The first one is what is outside the bracket, which is 1 divided by x squared. And the second one is what is inside the bracket, which is 3 plus 5x plus 2x squared. So I'll let u to be equal to the first one, which is 1 divided by x squared, which can be written as x exponent negative 2 from indices. And then v to be equal to what is inside the bracket, which is 3 plus 5x plus 2x squared. We are differentiating u with respect to x. The function is u is equal to x exponent negative 2. So from the general rule, we know that the du dx will be equal to the negative 2 will drop. So you have negative 2, and then negative 2 will reduce by 1. The exponent will reduce by 1. So we have negative 2 minus 1, which will give us negative 3. And from indices, we know that this can be written as negative 2 divided by x exponent 3. So when you find du dx, you have negative 2 divided by x exponent 3. Now let's find the v dx. We will differentiate each term. When we do that, when you differentiate 3, it's a constant, so you get 0. You differentiate 5x, because it's of the form ax, the x will be gone, you'll be left with a, which is the coefficient. So here, you differentiate 5x, you get 5. When you differentiate 2x squared, the 2 will drop and multiply. The exponent on x, which is 2, reduced by 1, so you have 4x. So the dv dx will be equal to 5 plus 4x. Now we can substitute that here. Dy dx is equal to u is x exponent negative 2, or 1 divided by x squared. So we have 1 divided by x squared into bracket. Dv dx is 5 plus 4x. Then minus v is 3 plus 5x plus 2x squared times du dx. Du dx is negative 2 into bracket x cubed. Now this, we can factor out 1 divided by x squared. When you factor out 1 divided by x squared, you have 1 divided by x squared into brackets 5 plus 4x, then minus 2 divided by x into bracket 3 plus 5x plus 2x squared. Remember, we have factored out 1 divided by x squared. When you open up the brackets, inside the brackets, you have 1 divided by x squared into bracket 5 plus 4x minus 6 divided by x minus 10 minus 4x. This gives us, when you simplify what is in the bracket, as you can see, 4x and negative 4x will be 0. 5 minus 10 will give us negative 5. And then we have minus 6 divided by x. So this gives us 1 divided by x squared into bracket negative 5 minus 6 divided by x. As I said before we solve this question, you could also just expand what you have here and then differentiate each term as we did in the previous examples. But here we wanted to use the product rule. If you have this in an exam and you are not comfortable with the product rule and the question does not restrict you to use the product rule, you can expand the bracket and differentiate each term as we did in the previous examples. Let's consider another question. Here we have x plus 5, that's the first term, and then being multiplied by x plus 2 squared. we are going to use the product rule, which is dy dx is equal to u dv dx plus v du dx. I'll let the first one, that's the first term, x plus 5, to be equal to u, so u is equal to x plus 5, and the second term, which is x plus 2 squared, be equal to v. When we expand x plus 2 squared, you have x squared plus 4x plus 4. Okay, now I'll need the u dx and the v dx. So I'll differentiate u with respect to x. That will give us 1, because when you differentiate x, you get 1. When you differentiate 5, you get 0. So du dx will be equal to 1. Then I'll also differentiate v with respect to x. We have 3 terms here, so you differentiate each term. When you do that, when you differentiate x squared, you have 2x. When you differentiate 4x, you have 4. And when you differentiate 4, you get 0. Okay. So the v dx is equal to 2x plus 4. Now let's substitute that here. We have u to be x plus 5, the v dx to be 2x plus 4. So we have x plus 5 times 2x plus 4. Then plus v is x plus 2 squared, and du dx is 1. So you have 1 times x plus 2 squared. And when you open this, you have 2x squared plus 14x plus 20 plus x squared plus 4x plus 4. When you simplify this, you have 3x squared plus 18x plus 24. Once again, if the question does not restrict you to use the product rule, you can easily expand x plus 2 all squared and then multiply it by x plus 5 and then differentiate each term, and you end up getting the same result. But if the question specifically says that you should use the product rule, then you will have to use the product rule. Let's consider the last question for product rule. So we have y is equal to 3x squared times 2x plus 1. I'm going to use the product rule here. The first term is 3x squared, and the second one is 2x plus 1. So I'll let u to be equal to 3x squared and v to be equal to 2x plus 1. We will need du dx, so I'll differentiate u with respect to x. When you do that, 2 will drop and multiply, and then x will reduce by 1. So you have 2 times 3x exponent 1, which will give us 6x. We also need the v dx. When you differentiate 2x, the x will be gone, you'll be left with 2. And when you differentiate 1, which is a constant, you get 0. So the dv dx is 2. Okay. Now we can substitute that here. When you do that, you have 3x squared times 2, because u is 3x squared and dv dx is 2. Then plus v is 2x plus 1, du dx is 6x, so you have 6x times 2x plus 1. When you expand what you have here, you have 3x squared times 2 gives us 6x squared, then plus 6x times 2x plus 1 gives us 12x squared plus 6x, and this gives us 18x squared plus 6x. Here too, you can easily expand this bracket and then differentiate each term as we did in the previous examples, and you get the same results. So this is the product rule. The product rule is giving us dy dx is equal to u dv dx plus v du dx. So if you have a function of the form y is equal to u v, or u times v, where both u and v are functions of x, then dy dx will be equal to u dv dx plus v du dx. So basically, the product rule is keep the first one, which is u. So look at it. Keep the first one, which is u, and then differentiate the second one, which is v, with respect to x. So dv dx. Then plus keep the second one, which is v, and differentiate the first one, which is u. So du dx. So keep the first one, differentiate the second one, plus keep the second one, differentiate the first one. That's the product rule. From the examples that we have just considered, we have learned how to use the product rule to differentiate a function. We are now going to learn how to use the quotient rule to differentiate a function. Sometimes you'll be given a quotient and you will have to use the quotient rule to differentiate. We will learn how to do that. Differentiation of a quotient. Let's consider this function y is equal to x plus 1 divided by x minus 1. As you can clearly see here, this is a quotient. It involves a division sign. How do we differentiate this? If you have a function of the form y is equal to u divided by v, and both u and v are functions of x, then the quotient rule says that dy dx will be equal to v du dx minus u dv dx divided by v squared. This is the quotient rule. If you have a function of the form y is equal to u divided by v, and both u and v are functions of x, then dy dx will be equal to v du dx minus u dv dx divided by v squared. So here, if we want to use the quotient rule to solve this, I'll call the numerator here u and the denominator v. Then I'll find u dx and find dv dx, and then after that I'll substitute the result of dv dx, du dx, v and u into this formula. Once again, the quotient rule is dy dx is equal to v, which is the denominator, du dx, minus u, which is the numerator, dv dx, divided by v, which is the denominator, squared. Okay, let's apply this to solve some questions. We have 4 questions here. We will take it one after the other. Let's consider the first one. Y is equal to 2 divided by 1 minus x squared. The quotient rule is dy dx is equal to v du dx minus u dv dx divided by v squared. The numerator is u and the denominator is v. So here I'll let u be equal to the numerator, which is 2, and v to be equal to the denominator, which is 1 minus x squared. When you expand 1 minus x squared, you have 1 minus 2x plus x squared. Now I'll need du dx and dv dx. Du dx, so you differentiate u with respect to x. Now here the function is u is equal to 2, which is a constant. We know that when you differentiate a constant, you get 0. So du dx will give us 0. For v, we have v is equal to 1 minus 2x plus x squared. So you differentiate each term. You find dv dx. You differentiate 1, you get 0. When you differentiate negative 2x, the x will be gone, so you'll be left with negative 2. When you differentiate x squared, you have 2x. So dv dx will be equal to negative 2 plus 2x. Now I have du dx, dv dx, I have u, I have v. So I can use the quotient rule to find dy dx. I'll substitute everything here. When you do that, you have du dx is 0, so 0 times v, which is 1 minus x squared, so 0 times 1 minus x squared, and then u is 2, so minus 2 into brackets dv dx, which is negative 2 plus 2x, so negative 2 plus 2x, divided by v squared. Remember, v is 1 minus x squared, so 1 minus x squared squared. Okay. When you simplify what you have on the numerator, you have 4 minus 4x. On the denominator, you have 1 minus x squared squared, and that gives us 1 minus x exponent 4. There is a common factor here that we can cancel. Look at it. We can factor 4 out here. When you do that, you have 4 into bracket 1 minus x. On the denominator, we have 1 minus x exponent 4. So 1 minus x on the numerator can cancel one of the 1 minus x here, and we'll be left with 3 of it. So this becomes 4 divided by 1 minus x exponent 3. So when you differentiate y with respect to x, for the function y is equal to 2 divided by 1 minus x squared, you have 4 divided by 1 minus x exponent 3. Let's consider the next question. We have y is equal to 3x divided by 1 plus x squared. This is a quotient, so we are going to use the quotient rule. The quotient rule says that dy dx will be equal to v du dx minus u dv dx divided by v squared. The numerator is always u and the denominator is always v. So here I'll let the numerator to be equal to 3x and the denominator to be equal to 1 plus x squared. We will need du dx and dv dx. So you have to differentiate u with respect to x and v with respect to x. U is equal to 3x. So if you differentiate 3x with respect to x, the x will be gone and you'll be left with 3. V is equal to 1 plus x squared. When you differentiate 1 plus x squared with respect to x, you differentiate 1, you get 0. You differentiate x squared, you get 2x. So du dx is 3 and dv dx is 2x. We now have u, v, du dx, dv dx. And so we can use the quotient rule to find dy dx. So the dy dx will be equal to du dx is 3 and v is 1 plus x squared. So we have 3 times 1 plus x squared, and then minus u is 3x, dv dx is 2x. So we have 3x times 2x. V is 1 plus x squared. So we have on the denominator, you have 1 plus x squared squared. When you expand the brackets you have on the numerator, you have 3 plus 3x squared minus 6x squared. And then on the denominator, you have 1 plus x squared squared. And this gives us 3 minus 3x squared divided by 1 plus x squared squared. Let's consider the next example. We have y is equal to 2x plus 3 divided by x minus 5. This is a quotient, so we are going to use the quotient rule. The numerator is always u, the denominator is always v. So here u will be equal to 2x plus 3 and v will be equal to x minus 5. We will find du dx and dv dx. So you differentiate 2x plus 3 with respect to x. You differentiate 2x, you get 2. 3 is a constant, so you get 0. Then we differentiate x minus 5 with respect to x. That will give us dv dx. You differentiate x, you get 1. You differentiate negative 5, you get 0 since it's a constant. We will now substitute that here. Du dx is 2. V is x minus 5. So you have 2 times x minus 5. Then u is 2x plus 3. Dv dx is 1. So we have minus 1 into bracket 2x plus 3. V is x minus 5, so x minus 5 squared. When you expand the brackets you have on the numerator, you have 2x minus 10 minus 2x minus 3. And this will be divided by x minus 5 squared. This gives us negative 13 divided by x minus 5 squared. Let's consider the next example, which is y is equal to 1 plus x squared divided by x minus 1. The numerator will be u, the denominator will be v. The quotient rule is dy dx is equal to v du dx minus u dv dx divided by v squared. U is 1 plus x squared, v is x minus 1. You need du dx, so you differentiate u, which is 1 plus x squared with respect to x. You differentiate 1, you get 0. You differentiate x squared, you get 2x. We also need dv dx. V is x minus 1. So you differentiate x with respect to x, that gives us 1. You differentiate negative 1, you get 0. So dv dx is 1. So now we have u, we have v, we have du dx, we have dv dx, and so we can substitute everything here. When you do that, you are going to have v is x minus 1, du dx is 2x, so you have 2x into bracket x minus 1, and then u is 1 plus x squared, dv dx is 1, so you have negative 1 times 1 plus x squared divided by v squared, and v is x minus 1, so x minus 1 squared. When you expand the bracket you have on the numerator, you have 2x squared minus 2x minus 1 minus x squared divided by x minus 1 squared. And this gives us x squared minus 2x minus 1 divided by x minus 1 squared. So this is how to use the quotient rule to differentiate a function. The quotient rule is dy dx is equal to v du dx minus u dv dx divided by v squared. Remember that the numerator is always u and the denominator is always v. If you look at the quotient rule carefully, that's how it goes like. You keep the denominator, which is v, then you differentiate the numerator, du dx. So you keep the denominator v, you differentiate the numerator, du dx, then minus, you keep the numerator u, you differentiate the denominator v, so dv dx, then after that divided by the denominator squared. So keep the denominator, differentiate the numerator, minus keep the numerator, differentiate the denominator, divided by the denominator squared. That gives us the quotient rule. Next, we are going to learn how to differentiate a function using the chain rule. What is the chain rule and when do we use it? Let's consider this example. Let's say we have this function y is equal to 3x exponent 4 minus 5 exponent 7. In the lesson on binomial theorem, we learned how to expand a function like this. So if we are to go by that, we will have to use what we learned under binomial theorem to expand this expression, and then we will differentiate each term. As you can see, since this is having an exponent of 7, that will be very tedious for us to do. So there should be an easier way or a quicker way for us to differentiate a function like this without going through the hassle of expanding this long expression and then differentiating each term. There is a method like that, and that is known as the chain rule. So with the chain rule, it helps us to differentiate functions like these. Sometimes you can have a function where the terms are under a square root sign. In that case too, you have to use the chain rule. It's easier to use the chain rule to differentiate. So what is the chain rule and how do we use it? The chain rule says that if y is a function of u and u is a function of x, then dy dx will be equal to dy du times du dx. See, let's consider this example here. We have y is equal to 3x exponent 4 minus 5 exponent 7. You see, this function here, 3x exponent 4 minus 5, we can let this function represent u. See, when we let this function represent u, we are going to have u is equal to 3x exponent 4 minus 5. Now, as soon as we do that, we can write y as y is equal to u exponent 7. So as you can see, y is now a function of u, and u is a function of x. because y is equal to u exponent 7 and u is equal to 3x exponent 4 minus 5. So if you have a function like this, then you can use the chain rule to differentiate. The chain rule basically says that dy dx is equal to dy du times du dx. So anytime you have a function like this, what you do is that you will let that term that is raised to the power a bigger number, you will let that be equal to u, or you let the term under the square root sign be equal to u. Then from there, you can write y as a function of u and u as a function of x, and then you use the chain rule to find it. Let's apply this to solve some questions. It's very interesting. Let's do that. We have 4 questions here. We will take it one after the other. Let's take the first one. We have y is equal to 3x exponent 4 minus 5 exponent 7. So we are going to use the chain rule here, which says that dy dx is equal to dy du times du dx. So what we will do is that the term that is raised to the power a bigger number, we will let that to be equal to u. So here the term is 3x exponent 4 minus 5. So we will let u to be equal to 3x exponent 4 minus 5. As soon as you do that, you can see that we can replace 3x exponent 4 minus 5 with u. And so you have y to be equal to u exponent 7. So we now have y as a function of u and u as a function of x. So you can use the chain rule. Our chain rule says that dy dx is equal to dy du times du dx. So you have to differentiate y with respect to u, and then we will differentiate u with respect to x. Let's start with differentiating u with respect to x. When you differentiate u with respect to x, we will differentiate each term. So you differentiate the first one, which is 3x exponent 4. We have learned that 4 will drop and multiply, and then the exponent 4 will reduce by 1, and that will give us 12x exponent 3. Negative 5 is a constant, so when you differentiate it, it will be 0. Now we will need dy du. So this time we are differentiating y with respect to u. So 7 will drop and multiply, and then the exponent 7 will reduce by 1. So when you differentiate y with respect to u, you have 7u exponent 6. Okay. Now we have dy du, we have du dx. So you can substitute it here. When you do the substitution, you have dy du is 7u exponent 6. Du dx is 12x exponent 3. When you multiply this, 7 times 12 gives us 84. So you have 84 x exponent 3 and then u exponent 6. But remember that we said u is equal to 3x exponent 4 minus 5. And so you have to bring it back. So when you bring it back, you have 84x exponent 3 into bracket 3x exponent 4 minus 5 exponent 6. So this gives us our dy dx. Now look at this. This is how the chain rule goes. The chain rule is basically differentiate what you have in the bracket times differentiate the whole bracket. This is what I mean by that. So look at this. Let's differentiate what we have in the bracket. We differentiate 3x exponent 4 minus 5. We know that when you differentiate 3x exponent 4, you have 12x exponent 3. Then times, we will differentiate the entire bracket as a whole. Now we are differentiating the entire thing, so 7 will drop. So you have 7. Then times, the exponent on the whole function will reduce by 1. So times 3x exponent 4 minus 5. The exponent 7 reduced by 1, and that will be 6. 12 times 7 gives us 84. So this gives us 84x exponent 3 times 3x exponent 4 minus 5 exponent 6. That's the chain rule. So the chain rule is always differentiate what you have in the bracket times differentiate the function as a whole. If you go through the process as we did, the chain rule is dy dx is equal to dy du times du dx. Let's consider the next question. Here we have y is equal to the square root of 1 minus 4x. We are going to use the chain rule. So we will let what is under the square root sign to be equal to u. The chain rule is dy dx is equal to dy du times du dx. So we will let what is under the square root sign, which is 1 minus 4x, to be equal to u. Now when we do that, we will have y will be equal to square root of u, because 1 minus 4x is now u. And square root of u, we know from indices that it can be written as u exponent half. Now we will need dy du and du dx. Let's first find du dx. So we are differentiating u with respect to x. When you differentiate 1, you get 0. When you differentiate negative 4x, you get negative 4. So du dx gives us negative 4. Let's differentiate y with respect to u to get dy du. For dy du, we will differentiate u exponent half. So half will drop and multiply. Then we reduce the exponent half by 1. That gives us half times u exponent negative half. And when you simplify this from indices, we know that this can be written as 1 divided by 2 root u. Okay. So now we have dy du and we have du dx, so we can substitute it here. When you do the substitution, you have 1 divided by 2 root u times negative 4. And this gives us negative 2 divided by root u, because the 2 here will divide negative 4, you have 2, and so you'll be left with negative 2 divided by root u. But remember that we said u is 1 minus 4x, so you have to bring it back. When you do that, you have negative 2 divided by square root of 1 minus 4x. So when you differentiate y with respect to x, you have negative 2 divided by square root of 1 minus 4x. Remember that I said the chain rule is basically differentiate what you have in the bracket, then times differentiate the entire function. So you see, let's write this. Let's write this in the brackets. So you have y will be equal to 1 minus 4x exponent half. Okay. Now to get the dy dx using the chain rule, we will differentiate what is in the bracket. What is in the bracket is 1 minus 4x. So when you differentiate that, you differentiate 1, you get 0. You differentiate negative 4x, you get negative 4. Then times, we will differentiate the entire function as a whole. So half will drop, and so you have half, it will drop and multiply. Then we reduce the exponent half by 1, and so that will be 1 minus 4x exponent half minus 1 will give us negative half. So here the 2 and we'll divide negative 4 by 2, and this will be equal to negative 2 times 1 is negative 2, then times 1 minus 4x exponent negative half. And we know that from indices, this can be written as negative 2 divided by 1 minus 4x exponent half. So the chain rule is always differentiate what is in the brackets, then times differentiate the entire function as a whole. Or you can go through the process that we have gone through here. The chain rule is dy dx is equal to dy du times du dx. Let's consider the next example. We have y is equal to 10 divided by 2x squared plus 1 exponent 5. So this involves a quotient, but we will still use the chain rule here. We will always make sure that what is under the square root sign or the cube root sign or the term that is having the higher exponent, we will let that be equal to u. So here the term that is having the higher exponent is 2x squared plus 1. So we will let that represent u. So u will be equal to 2x squared plus 1. When we do that, y will be equal to 10 divided by u exponent 5, which can be written as 10 u exponent negative 5. We will need dy du, and we also need du dx. So we will differentiate u with respect to x, and we differentiate y with respect to u. Let's start with du dx. For du dx, we have 4x. When you differentiate 2x squared, you have 4x. You differentiate 1, you get 0, since it's a constant. Then we also differentiate y with respect to u. Remember that y is equal to 10 u exponent negative 5. So the negative 5 will drop and multiply. That will give us negative 50. And then we reduce the exponent of u, which is negative 5, by 1. So you have negative 5 minus 1, which gives us negative 6. So you have negative 50 u exponent negative 6. And this can be written as negative 50 divided by u exponent 6. Now we can substitute them here. When you do that, we have negative 50 divided by u exponent 6 times 4x. This gives us negative 200x divided by u exponent 6. Remember, we said u is 2x squared plus 1, so you have to bring it back. And so when you bring it back, you have negative 200x divided by 2x squared plus 1 exponent 6. Once again, as I said, the chain rule is always differentiate what is in the bracket times differentiate the entire bracket. See here, we have y is equal to 10 divided by 2x squared plus 1 exponent 5. From indices, we know that this can be written as y is equal to 10 into bracket 2x squared plus 1 exponent negative 5. Okay, so to get the dy dx, we will differentiate what is in the bracket. What is in the bracket is 2x squared plus 1. When you differentiate that, you have 4x. Okay, then times, we will differentiate the whole fraction, right? The whole fraction, so the negative 5 will drop and multiply. When the negative 5 drops and multiply, you have negative 5 times 10, which will give us negative 50. And then this gives us 2x squared plus 1 exponent negative 6, because you reduce the exponent here, which is negative 5, by 1. So that will be exponent negative 6. Okay. 4x times negative 50 gives us negative 200. So you have negative 200x. And then this becomes 2x squared plus 1 exponent negative 6. And from indices, we know that this can be written as negative 200x divided by 2x squared plus 1 exponent 6, just as we have here. So all the time, the chain rule is differentiate what is in the bracket times differentiate the whole function, and you get the same result as you go through the process here, using dy dx is equal to dy du times du dx. Let's consider the next example under chain rule. We have y is equal to 1 divided by square root of 3 minus x. Here too we can use the chain rule. Always make what is under the square root sign u. Okay. So here what is under the square root sign is 3 minus x. So we will let u to be equal to 3 minus x. When we do that, we can write y as y is equal to 1 divided by square root of u, which can be written as 1 divided by u exponent half, which is u exponent negative half from indices. Now we will need dy du and du dx. So you find du dx and dy du. Let's begin with du dx. You differentiate 3, you get 0. You differentiate negative x, you get negative 1. For dy du, we are differentiating y with respect to u. So dy du will be equal to, the negative half will drop, so you have negative half, and then you reduce negative half by 1, so that is going to be negative half minus 1, and that will give us negative 3 divided by 2. So this gives us negative half negative half times u exponent negative 3 divided by 2. From indices, this will give us negative 1 divided by 2 root u cube. Okay. When you do this, you have negative 1 divided by 2 root u cube. Because, let's look at it. You see, we have negative half u exponent negative 3 divided by 2. Okay, so this will be equal to negative 1 divided by 2 u exponent 3 divided by 2. Now, u exponent 3 divided by 2 is basically u exponent 3 exponent half, right? And we know that anything exponent half can be written as the square root of that thing. So this is square root of u exponent 3. Okay. And that is why this becomes minus 1 divided by 2, and then the square root of u exponent 3. And so dy du is negative 1 divided by 2 root u exponent 3. We discussed this in details in the lesson on indices, so you can go and check it out. Now we can substitute them here. When you do that, we have negative 1 divided by 2 root u exponent 3 times negative 1. And this gives us 1 divided by 2 root u exponent 3. But remember, we said that u is 3 minus x. So when you bring it back, you have 1 divided by 2 root 3 minus x cube. So when you find dy dx, you have 1 divided by 2 root 3 minus x cube. Once again, as I said, the chain rule is always differentiate what is in a bracket times differentiate the entire bracket as a whole. So let's apply that here and see. This can be written as y is equal to 3 minus x exponent negative half. Okay. Now we will differentiate what is in the bracket. So the dy dx will be equal to, when you differentiate what is in the bracket, you differentiate 3, you get 0. You differentiate negative x, you get negative 1. So negative 1 times, then we will differentiate the entire function as a whole. So negative half will drop and multiply, so you have negative half. Then you reduce the exponent here by 1. And so that would be 3 minus x exponent negative half minus 1. And that will give us negative 3 divided by 2. Okay. This gives us negative 1 times negative half gives us positive half. So this will be positive half. Then 3 minus x exponent negative 3 divided by 2. And this can be written as 1 divided by 2 times 3 minus x exponent 3 divided by 2. And as we have just learned, this is basically 1 divided by 2 root 3 minus x exponent 3. So all the time, the chain rule is differentiate what is in the bracket times differentiate the entire bracket. When you go through the process that we have gone through here, you end up getting the same thing. The chain rule is dy dx is equal to dy du times du dx. From the examples that we have considered, we now know what the chain rule is. We know how to use it and when to use it. We are now going to learn how to differentiate implicit functions. We will learn what implicit functions are and how to differentiate it. Differentiating an implicit function. First, let's consider what an implicit function is. An implicit function in two variables x and y is one in which neither can be easily expressed in terms of the other. You see, in the previous examples that we have considered, for all the functions that we have differentiated, you can see that one variable can be expressed as the subject of the equation, or one variable can be expressed in terms of the other easily. So, for example, we can have something like y is equal to 3x squared plus 1. As you can clearly see here, y is the subject of the equation, so we can go ahead and differentiate. All the examples that we have considered is like this. But we have some functions that expressing one variable as the subject of the equation, or expressing one variable in terms of the other, is quite tedious. You can't do that easily. Such examples are known as implicit functions. An example is what we have here. We have x squared plus y squared is equal to 2xy. We are going to learn how to differentiate a function like this when you meet one. Differentiating an implicit function is quite similar to what we have already studied. There are some few things that you need to take note of though. One of them is that we are going to differentiate each term in the equation. So if we consider the example here, we have x squared plus y squared is equal to 2xy. We will differentiate each term. So you differentiate x squared, you differentiate y squared, and then we differentiate 2xy. Another thing that you have to also take note of is that if a term contains a product, then you have to differentiate it as a product. So here we have 2xy. Okay, so we will have to differentiate 2xy as a product because it's a product. Okay, so we are going to apply the product rule here. Because we have a product, we will differentiate it as a product. Another thing that you have to also take note of is that when you differentiate a term containing y, you have to indicate that by adding dy dx to it. Okay, so this is what I mean. You see, in the previous examples that we have considered, let's say we have a function like this, y is equal to 3x squared. Okay, and we are being told to differentiate this. When we are differentiating this, we will differentiate what we have on the left and then we differentiate what we have on the right. So we will begin by differentiating y with respect to x. You see, from the general rule of differentiation that we learned, if we take y and we are differentiating it, we know that the exponent on y will multiply. So here the exponent of y is 1, so it will drop and multiply. So we have 1 times. Then we reduce the exponent by 1, so y exponent 1 minus 1. 1 minus 1 gives us 0, so this will be y times y exponent 0, and this is equal to 1. Since y exponent 0 is 1, so you have 1 times 1, which is 1. So when you differentiate y, you get 1. But because y is a term containing y, we have to indicate that by adding dy dx to it. So actually, we have 1 dy dx to show that we have actually differentiated a term containing y. And that is why when you differentiate y, you get dy dx, because 1 times dy dx gives us dy dx. So in the differentiation that we are going to do here, that is under implicit functions, anytime you differentiate a term containing y, you have to indicate that by multiplying it by dy dx. Maybe you are wondering, why don't we do the same when we differentiate a term containing x? So for example, here, if we are differentiating the right hand side, why don't we add something like dy dx or dx dx to it? Now look at it. You see here, if you are differentiating a term containing x, you are actually differentiating with respect to x. So you are differentiating x with respect to x. So here, if we go through the normal differentiation process, 2 will multiply, so we have 2 times, then 3x, the exponent will reduce by 1, so 2 minus 1. And this gives us 2 minus 1 is 1. So we have 2 times 3x exponent 1, which gives us 6x. But actually, what we are doing here is that we are differentiating x with respect to x. So it is dx, which ends up cancelling to give us 1. So that would be 6x times 1, which is 6x. So when we differentiate a term containing x with respect to x, we are doing the differentiation with respect to x. So the dx and dx ends up cancelling each other. Okay. But when you differentiate a term containing y with respect to x, you have to indicate that you are differentiating a term containing y with respect to x. So we always multiply it by dy dx. Okay. Now that we have this out of the way, we can take some examples on differentiating implicit functions. So let's do that. We have 4 examples here. We will take it one after the other. Let's begin with the first one. It says that find dy dx if x squared plus y squared is equal to 3. The equation is x squared plus y squared is equal to 3. We will differentiate each term. So we begin with the first one, x squared. When you differentiate x squared, we know that the 2 will drop, and so you have 2 times and then x exponent. The exponent on x will reduce by 1, so 2 minus 1, which will be 2 times x exponent 1, which is 2x, as we can see here. When you differentiate y squared, we know that the 2 will drop, so you have 2 times then y, the exponent 2 reduced by 1, so 2 minus 1, and this will be 2 times y exponent 1, which is 2y. But because it is a term containing y, you have to indicate that by multiplying it by dy dx, as you can see here. And this is equal to, when you differentiate a constant, which is 3, you get 0, and so that will be 0. We have 2x plus 2y dy dx is equal to 0. We will get dy dx by making it the subject of this equation. So I'll move 2x from the left-hand side to the right-hand side. So the equation becomes 2y dy dx is equal to negative 2x. I'll divide both sides by 2y. So I'll divide the left-hand side by 2y, the right-hand side by 2y. And so dy dx will be equal to negative 2x divided by 2y. And when you simplify this, dy dx is equal to negative x divided by y. Let's consider the next example. It says we should find dy dx if x cubed plus y cubed is equal to 3xy. So the equation is x cubed plus y cubed is equal to 3xy. We will differentiate each term. Let's begin with the first one, which is x cubed. When you differentiate x cubed, you have 3x squared. The 3 will drop and multiply. So you have 3x, and then the exponent 3 will reduce by 1, so 3x squared. We move on to the next one, which is y cubed. When you differentiate y cubed, you actually have 3y squared. The 3 will drop and multiply. The exponent 3 will reduce by 1, so we have 3y squared. But because it is a term containing y, you have to indicate that by multiplying it by dy dx. Okay, and this will be equal to, now here we have 3xy. As you can see, 3xy is a product, so we are going to treat it as a product. We will use the product rule. Remember the product rule? Dy dx is equal to u dv dx plus v du dx. Okay, so here we have to indicate what will be u and what will be v. Now that's what I'll do. I'll separate 3xy into 3x times y, right? 3x times y. So when I do that, I'll treat the 3x as u and then the y as v. You see, from the product rule, it says u dv dx plus v du dx. So keep the first one, differentiate the second one, keep the second one, differentiate the first one, just as we learned under product rule. So that is what we are going to do here. And so we will start. We have u is 3x, so 3x, then times, differentiate the second one, which is v. V is y, so we are going to differentiate y. When you differentiate y, you have 1. But because it is a term containing y, we have to multiply it by dy dx. Okay. Then we move on to the next one, which is keep the second one, that is keep v, differentiate the first one, that is differentiate u. Once again, v is y, so it's going to be plus y, then times, we differentiate 3x. When you differentiate 3x, that gives us 3. Okay, so we have 3x times 1 dy dx, which is the same as dy dx, then plus y times 3, as you can see here. So I'll quickly go over this in case you missed something here. 3xy is a product, so we have to treat it as a product. Okay, so what I will choose to do here is that I will separate 3xy into 3x times y. So the 3x becomes my first term, which is u. The y becomes the second term, which is v. From the product rule, we know that it is u dv dx plus v du dx. So you keep the first one, which is u, you differentiate the second one, which is v. Then plus, you keep the second one, which is v, you differentiate the first one, which is u. So the u here is 3x. That's what we have here. Then times, you differentiate v, but v is y. We know that when you differentiate y, you get 1. But because it is a term containing y, you have to multiply it by dy dx, as we have here. Then plus, we move on to v. V is y, so you have that here. Then times, you differentiate u. U is 3x. When you differentiate 3x, you have 3, just as you can see here. Now we can simplify and then find our dy dx. This gives us 3x squared plus 3y squared dy dx is equal to 3x dy dx plus 3y. To make dy dx the subject, I'll group all the terms containing dy dx on one side and the terms without dy dx on the other side. This gives us 3y squared dy dx minus 3x dy dx is equal to 3y minus 3x squared. I'll factor dy dx out. That will give me dy dx into bracket 3y squared minus 3x is equal to 3y minus 3x squared. You now divide both sides by 3y squared minus 3x, and that gives us dy dx is equal to 3y minus 3x squared divided by 3y squared minus 3x. As you can see, 3 is a factor on both the numerator and the denominator, so you can factor it out and cancel. When you do that, you have dy dx is equal to y minus x squared divided by y squared minus x. Let's consider the next example. Find dy dx if x squared plus y squared minus 2x plus 3y plus 6 is equal to 0. So here the equation is x squared plus y squared minus 2x plus 3y plus 6 is equal to 0. If you remember from the lesson on circles, this is an equation of a circle. X squared plus y squared minus 2x plus 3y plus 6 is equal to 0. We are going to find dy dx. We will differentiate each term. So let's begin with the first one, x squared. When you differentiate x squared, you have 2x. When you differentiate y squared, you have 2y. But because it is a term containing y, we have to multiply it by dy dx. Always remember that. The next one is negative 2x. When you differentiate negative 2x, you have negative 2. The x should be gone. The next one is 3y. When you differentiate 3y, you have 3. The y will be gone. But because it is a term containing y, you multiply it by dy dx. 6 is a constant, so when you differentiate it, you get 0. 0 is a constant. When you differentiate it, you get 0. So we now have 2x plus 2y dy dx minus 2 plus 3 dy dx plus 0 is equal to 0. We want to make dy dx the subject, so I'll group all the terms with dy dx on one side and the other terms on the other side. This gives us 2y dy dx plus 3 dy dx is equal to 2 minus 2x. I'll factor dy dx out. So I'll have dy dx into bracket 2y plus 3 is equal to 2 minus 2x. Divide both sides by 2y plus 3, and so dy dx will be equal to 2 minus 2x divided by 2y plus 3. Let's consider the last example. If x squared plus y squared is equal to py times y plus x squared, where p is a constant, take note of that because it's very important. P is a constant, find dy dx. Here the equation is x squared plus y squared is equal to py times 1 plus x squared. We are going to find dy dx, so we will differentiate each term. Let's begin with the first one, which is x squared. When you differentiate x squared, you have 2x. Then plus, when you differentiate y squared, you have 2y. But it is a term containing y. And anytime we differentiate a term containing y, we have to multiply it by dy dx. And this will be equal to, now here's where it gets interesting, so pay attention here. You have py times 1 plus x squared. Now this is a product, so we have to treat it as a product. So we are going to apply the product rule here. From the product rule, we know that when we differentiate, we are going to have u dv dx plus v du dx. Okay. Now I'll write py times 1 plus x squared. I'll write it such that I'll be able to get my u and my v. I'll separate it as py times 1 plus x squared. So here the py becomes u and the 1 plus x squared becomes v. The py is u and then the 1 plus x squared is v. Remember that p is a constant. Okay. So if py is u and 1 plus x squared is v, if we are using the product rule to differentiate here, we will have to keep u, right? We keep u, and u is py. So we keep py, then times, we differentiate the second one, that is v. We differentiate 1 plus x squared. When you differentiate 1 plus x squared, you get 2x, because when you differentiate 1, you get 0. You differentiate x squared, you get 2x. So we now have py times 2x. Then plus, we will keep v. V is 1 plus x squared. So we keep 1 plus x squared. Then we will differentiate u. U is py. But remember that p is a constant. So it is as if, let's assume that maybe p is 3. Let's just assume that p is 3. See, if p is 3, you have 3y. And when you differentiate 3y, you have 3. But because it's a term containing y, you multiply it by dy dx. If, let's say, p is 5, you have 5y. When you differentiate 5y, you have 5, and then you multiply it by dy dx because it's a term containing y. So you can see the trend here. If you differentiate a constant, then y, you are always going to have the constant and then dy dx. So if p is a constant and you differentiate py with respect to y, then it's going to be the constant p and then dy dx. So it's the same way. When it's 3y, it's 3 dy dx. When it's 5y, it's 5 dy dx. When it's negative 2y, it's negative 2 dy dx. So if p is a constant and it's py, then it's going to be p dy dx. Okay. Now that we have that, let's simplify and find dy dx. When we do the simplification, we have 2x plus 2y dy dx is equal to py times 2x gives us 2pxy, then plus, this can be written as dy dx p 1 plus x squared. We need dy dx, so we let all the terms containing dy dx go on one side and then the other terms on the other side. When you do that, you are going to have 2y dy dx minus dy dx p 1 plus x squared is equal to 2pxy minus 2x. When I factor dy dx out, I'll have dy dx into brackets 2y minus p times 1 plus x squared is equal to 2pxy minus 2x. You divide both sides by 2y minus p times 1 plus x squared, and you have dy dx is equal to 2pxy minus 2x divided by 2y minus p times 1 plus x squared. So this is how to differentiate implicit functions. You differentiate each term in the function. If you have a product, you differentiate it as a product using the product rule. And always remember that when you differentiate a term containing y, you have to indicate that by multiplying it by dy dx. Now let's consider the last objective for this lesson, which is higher derivatives. So far, all the derivatives we have been finding are first derivatives. What do I mean by that? Let's say we have the function y is equal to 3x squared plus 1, and you find dy dx. You know, when you find dy dx, you get 6x. Okay. You see, we have differentiated the function once. This is the first time that we are differentiating the function. We had y is equal to 3x squared plus 1, and we found dy dx. We have differentiated it once. When you differentiate a function for the first time, it is known as a first order derivative. So here, when you find dy dx, the dy dx is a first order derivative. Sometimes, after differentiating a function for the first time, you may be asked to differentiate the same function again. When you differentiate the function for the second time, it is known as a second order derivative. When you differentiate it for the third time, it's known as a third order derivative, and the order continues. So the fourth time will be the fourth order, the fifth time will be the fifth order, and so on and so forth. So when you have a function and you differentiate it for the first time, it's known as a first order derivative. So the dy dx is a first order derivative. When you differentiate it for the second time, it is a second order derivative. When differentiated for the third time, it is a third order derivative. Okay. So if y is a function of x, then dy dx or f prime of x is known as a first order derivative. When you differentiate the same function again, that is the differentiated function, right? The result that you got after you differentiated the function for the first time, if you differentiate that result again, then it is known as a second order derivative, and it is written as d squared y dx squared. Take note of this. It is d squared y dx squared. It is different from dy dx all squared. It's not the same. Dy dx all squared means that the function that you have differentiated for the first time, square it. But d squared y dx squared means that the function that you have differentiated for the first time, differentiate it again. Okay, so this is what I mean. Let's go back to our example. Let's say we have y is equal to 3x squared plus 1. Okay. Now, when you find dy dx, you are going to have 6x. Okay. If the question says that find dy dx all squared, what it means is that this 6x square it. So your dy dx all squared will be equal to 6x squared. And this gives us 36x squared. But if the question says find d squared y dx squared, d squared y dx squared, what it means is that this 6x that you have, differentiate it again, right? When you differentiate 6x, you are going to get 6. You see the difference? Dy dx all squared means that when you differentiate it, square your results. Okay, that's not what we are talking about here. What we have here is d squared y dx squared. which means that the function that you have differentiate it again. So that will give you the second order derivative. And as you can see here, the second order derivative can also be denoted as f prime prime of x. The first order derivative is f prime of x. The second order derivative is f prime prime of x. In some books, you see it as y prime prime. So the first order derivative can be written as y prime. The second order derivative as y prime prime. It's the same thing. But if you are writing it in the Leibniz notation, it's going to be d squared y dx squared. If you differentiate the second order derivative again, it's going to be d cube y ds cube. And if you are writing it in the functional notation, it's going to be f prime 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 of x. And the order continues on and on. Let's take a couple of examples here and apply this. We have 3 examples here. We will take it one after the other. Let's begin with the first one. So for the first one, we have f of x is equal to x cubed plus 2x squared minus 5x plus 4. And the question says we should find f prime prime of x, which means that we should find the second order derivative. So we will differentiate the function for the first time, and then we will differentiate it again. Okay. So f of x is x cubed plus 2x squared minus 5x plus 4. You differentiate it for the first time. You differentiate x cubed, you have 3x squared. You differentiate 2x squared, you have 4x. You differentiate negative 5x, you have negative 5. You differentiate 4, you get 0. But we want f prime prime of x, which is the second derivative. So this function, we will differentiate it again. Okay. And when we do that, we are going to have, you differentiate 3x squared, you get 6x. You differentiate 4x, you get 4. You differentiate negative 5, you get 0. So f prime prime of x gives us 6x plus 4. Remember that this f prime prime of x, if you write it in the Leibniz notation, is written as d squared y dx squared. Okay. If the question had said we should find the third derivative, then we will differentiate this function again. Okay. Let's consider the next example. If y is equal to 1 divided by x cubed, then find d cube y dx cube, right? So here we are going to find the third order derivative. So you differentiate the function for the first time, you differentiate it for the second time, and then you differentiate it for the third time. The function given to us is y is equal to 1 divided by x cubed, which can be written as x exponent negative 3 from indices. Let's differentiate it for the first time. If we differentiate it for the first time, we know that this gives us negative 3 x exponent negative 4, because the negative 3 will drop and multiply, and then we reduce the exponent, which is negative 3, by 1. So we have negative 3 x exponent negative 4. Now this gives us the first order derivative. We will have to differentiate this function again. So we will take the second order derivative. So you differentiate negative 3 x exponent negative 4 again. The negative 4 will drop and multiply. So you are going to have negative 3 times negative 4. And then the exponent, which is negative 4, will reduce by 1. Negative 3 times negative 4 gives us 12. Negative 4 minus 1 gives us negative 5. And so this gives us 12x exponent negative 5. We are looking for the third order derivative, so we have to differentiate 12x exponent negative 5. So negative 5 will drop and multiply, and so you have negative 5 times 12, which will give us negative 60. And then we will reduce the exponent 5 by 1. Negative 5 minus 1 gives us negative 6. And so this gives us negative 60x exponent negative 6. And we know that from indices, this can be written as negative 60 divided by x exponent 6. Let's consider the last example. If y is equal to 1 plus 2x divided by 1 minus 2x, find d squared y dx squared in its simplest form. Okay. So here we have a quotient, and so we are going to differentiate this using the quotient rule. So the first derivative, we are going to differentiate using the quotient rule. Remember that from the quotient rule, we have v du dx minus u dv dx divided by v squared. And always the numerator is u, the denominator is v. So I'll let the numerator, which is 1 plus 2x, be equal to u, and the denominator, which is 1 minus 2x, be equal to v. We will need du dx and dv dx, so you have to find du dx. When you differentiate u with respect to x, you differentiate 1, you get 0. You differentiate 2x, you get 2. When you differentiate v with respect to x, you have dv dx is equal to, you differentiate 1, you get 0. You differentiate negative 2x, you get negative 2. The quotient rule says that dy dx is equal to v du dx minus u dv dx divided by v squared. Okay, so let's substitute the information in. Du dx is 2. V is 1 minus 2x. So you have 2 times 1 minus 2x. Then minus u dv dx. I'll bring the dv dx first. Multiplication is commutative, so it doesn't matter which one I'll bring first. The dv dx is negative 2. So I'm going to have minus negative 2. And that gives us positive 2. So plus 2. Then u is 1 plus 2x. So 2 times 1 plus 2x. Divided by v squared. V is 1 minus 2x. So 1 minus 2x squared. When you open the brackets on the numerator, you have 2 minus 4x plus 2 plus 4x divided by 1 minus 2x squared. Negative 4x plus 4x is 0. And so this gives us 4 divided by 1 minus 2x squared. But remember, this is the first derivative. This is the dy dx. We are looking for d squared y dx squared. So you have to differentiate this again. The result that we have here, we have to differentiate it again. We know that dy dx is equal to 4 divided by 1 minus 2x all squared. There is a quotient, so I'm going to use the quotient rule again. You can also choose to use the chain rule. You can use the chain rule here to differentiate and you end up getting the same thing. But here I'm going to use the quotient rule. The numerator is 4, so I'll let u to be equal to 4. The denominator is 1 minus 2x squared. So v is equal to 1 minus 2x squared. When you expand this, you are going to have 1 minus 4x plus 4x squared. You need du dx and dv dx. So I'll have to differentiate u with respect to x and v with respect to x. When you differentiate u with respect to x, you have du dx is equal to, you differentiate 4, you get 0 because 4 is a constant. You are differentiating v with respect to x. You differentiate v with respect to x, you have dv dx. You differentiate 1, you get 0. You differentiate negative 4x, you have negative 4. And differentiate 4x squared, you have 8x. So now I have du dx, I have dv dx, I have u, and I have v. So I can find the second derivative using the quotient rule. So from the quotient rule, this time the second derivative, which is d squared y dx squared, will be equal to v du dx minus u dv dx is equal to v squared. The reason why I have d squared y dx squared here is that we have already differentiated the function. So this is the second derivative. Okay. And so that would be d squared y dx squared. Let's substitute the information in it. Du dx is 0. So I have 0 times v, which is 1 minus 2x squared, which will end up being 0 because you are multiplying everything by 0. And then u is 4. Dv dx is negative 4 plus 8x. So you have negative 4 into bracket, negative 4 plus 8x divided by v is 1 minus 2x squared. So 1 minus 2x squared because the denominator here is v squared. When you simplify what you have on the numerator, 0 times this will give you 0. Negative 4 times negative 4 gives 16. Negative 4 times 8x gives negative 32x. Divide this one by 1 minus 2x exponent 4. We can factorize what you have on the numerator. When you factorize it, you have 16 into bracket 1 minus 2x. And this will be divided by 1 minus 2x exponent 4. 1 minus 2x on the numerator can cancel one of the 1 minus 2x on the denominator. And when you do that, you have 16 divided by 1 minus 2x exponent 3. So for this function, y is equal to 1 plus 2x divided by 1 minus 2x. When you find the second derivative, which is the d squared y dx squared, you have 16 divided by 1 minus 2x exponent 3. This is the end of the lesson on differentiation. Thank you for watching this video. Subscribe to this channel for more videos. See you in the next one. Bye-bye.